Good morning again to everyone. How was yesterday?
Hello.
Perfect. The YouTube is live. Okay, so I'll leave the floor to Yosha, who's going to start with his lecture. As I said, today, Yosha will be talking about KPIs, multidisciplinary analysis, and generative design in Grasshopper. So I will leave the floor to you, Yosha.
Yes.
Super. And yeah, enjoy, and I'll see you in a bit.
Oops. Yeah, I'm bringing up my slides. So I will start with a little presentation, and then we will make a break. And we have a hands-on Grasshopper. I show you a script I just shared in the Slack file. You can already download it if you want. And essentially, we're combining yesterday's file with the InFraReD web integration with mostly actually decoding spaces components for network analysis, maybe some ISOVIS, some visual sightlines analysis all together. And I will show a case study using the Barcelona site as an example how you could approach the whole idea of having a data-driven design project. Good. I'll share my screen. All good. Oh, who's host? I can't share my screen.
Angelos, could you co-host the rest of us if you're still here? He's might have gone. Uh-oh. I'll shoot him a message.
Yeah, let's do it in Slack maybe.
Yeah, I closed the window in the meantime. Well,
Yosh, you should be co-host now. Give it a go.
yeah, now it looks good. Whoops. Yeah. So we started a bit on this field, computational analysis and design. It's a bit more detailed than yesterday, and yeah, how to employ and combine several Grasshopper plugins to do that on this Barcelona dummy case study we had shown. So the general idea is that we get a digital representation of insight and run simulations on them in order to get measurable insights on the characteristics and performance of the site and the design we propose on it. So now with the ability to quickly assess different urban design solutions, we can engage in an iterative design process and adjust our designs according to this data feedback we get. And of course, this only really works if the simulation engines are somewhat fast enough. Otherwise, if you wait for hours, this is not really feasible that much. Yeah, the tricky part is to prepare the data, the maps, but also define what we actually want to measure, as kind of mentioned already yesterday, and which indicators to choose to evaluate, and also to define what is good and bad. So we can have a bunch of indicators like wind, as we had yesterday, but it's still discuss about what is good, what is bad. I mean, maybe some areas have very high wind speeds, a storm day or something, then you want your built environment somehow to protect maybe the pedestrian level from too stark of winds, dangerous wind levels. If you're in a very hot region, you might want actually to create some wind tunnel effects to kind of have a fresh breeze in there. So this is really context specific. And something, yeah, one has to think of always project specific. So nevertheless, if we manage to define a set of meaningful indicators to simulate and manage to simulate them and also know how to interpret them, we can have more or less a data-driven approach and can evaluate different design options according along different criteria. Now it gets more interesting about thinking generative and parametric urban design at the same time, especially if we have this kind of setup, because now we can ask, theoretically at least, ask the computer to design a bit for us and let it try to automatically optimize our proposals. In case we said like certain criteria are definitely more is better or less is better. This is kind of clear definition. And a simple example shown here, we want to find the best location for a bus stop, for instance. Our performance indicator is the aggregate distance from the bus stop to all houses around here, and which you want to minimize so that most people have the aggregate distance of people walking to the station is minimal. So high accessibility. Now this simple tasking algorithm can do that in Grasshopper, for instance, Galapagos, and the only design parameter we actually have is an XY coordinate of the bus stop. We can just kind of randomly or more systematically shift it around. Then we see somehow how the simple score performs. And we kind of can get a feeling what the computer does it for us to find a more better position for that. With a combination of X and Y in this case. So a bit more complex. This is a case study we did, a similar paper last year, I think, where we combined a parametric model with a bit more diverse set of performance indicators. And yeah, here you see the parametric model in action. Essentially, you have this multiple blocks here. A street segment is rotating in the middle. The other ones are generated automatically. And then we run I think we have 6 fitness objectives and 4 simulation engines running in the background, including the CFD simulation you see here. And we have a quite big chunk of context here because we did some accessibility analysis as well, where it's more about how people move through the quarter and how accessible it is to other guys around here. Then we couple it with an evolutionary optimization algorithm, Octopus, also Grasshopper plugin, and that helped us to explore the design space for us. Yeah, and finally, we used this inputs, this kind of explore design space to know, okay, what is the best possible wind performance based on our optimization algorithm, and use these information for manual design. So it gave us some feedback, okay, you perform maybe or the best option the computer found is 10% better than what you have just now manually designed. So this is kind of a good guidance to get a feeling, okay, there's more possible, or I'm actually performing kind of well with this manual design, because in the end, parametric models will always be quite limited. You have to set, at least for now, nowadays you have to set them up manually. You have a few parameters input, and they usually don't really deliver that diverse outputs. So at the end of the day, I think usually people end up doing a lot manual there. So I think this I showed already yesterday. It's a very important step that in setting up a parametric model and analytical modules to evaluate its output. So the first step is, again, to think about a vision or design goals or design problem from which we can derive strategical key goals. And that can be tangible things like providing a certain amount of residential units, or more abstract things such as promoting walkability, 15-minute city, for instance, like those kind of things, or the aim to become a vibrant, integrated local center. Then the next step is to operationalize these abstract goals into actionable strategies before finally defining indicators to quantify the degree of success. And of course, the most important part here is the term quantifying, because these needs to be numbers that we can easily measure and express in simple terms. Last but not least, which can also help highlighting in colors on the right-hand side, is which parameter of the parametric model or manual made model assumingly affect the indicator. So red is represents building volumes, blue the network, street network configuration, and green a bridge. This is like case study specific. So this is also good to keep in mind to know how you can kind of affect these indicators, and if you have any means to actually have an impact on them. For this example, these are kind of the parameters we have to change. We are able to change a rotating street segment, kind of the orientation of the block streets and layout. Then a pedestrian overpass location, there were just 4 options, and then the building volume, the height of the building volumes. That's all what was altered by the algorithm. Now we have a parametric model and some indicators, but it's still not precise enough. So we have to be even more specific than that. We can also say, okay, we have maybe now a CFD simulation, we maybe have a mobility simulation, but we need to really come to something you could call key performance indicator, kind of one number. And I want to illustrate this a bit. Let's have a closer look on this one. This is kind of a raw analysis results. It's for this example, I choose a noise map. It's kind of like CFD. We have something like a bitmap on array here with around 400,000 individual data points or pixels depicting the noise level for each square meter in space. Now, 400,000 data points is a lot of information. So comparing one solution, one scenario with 1 or 2 variants might work for humans. For us visually, we can kind of train to do that. For a computer, it's already a bit more complex. But when it comes to comparing a few thousands or even hundreds of them, this is even for a human too complex, not to speak about optimization algorithms like Octopus that usually take around maybe 8 parameters at max, at best. So we need to drastically reduce and simplify information we get as a raw output from simulation engines like this noise or CFD. The approach is quite straightforward. A first step could be we kind of decide what areas we actually care about. So this case, we say we don't care. We only care about the noise stress in residential areas. So we'd say we don't care about the middle of the streets, how noisy it's there. We only take a subsample of our data set, which in this case kind of this residential areas around buildings. This say reduces our data points to 250,000 points, which is still way too much. And so at the very end, we usually have to condense all of this massive amount of points and data points into a single number, maybe 2 or 3. And this is what we would refer to as key performance indicators. So we take all this information and turn it, let's say, into the average. So we take the average noise level for this area, or we take the median noise level for this area. Or we say, give me the percentage of areas that have a noise level over 75 decibels. Now, doing that is a bit tricky. Let's say we take the full result we have here and just compute the mean for it, then the mean will probably show something, everything looks okay, because we have here a very silent area and here a few very noisy areas. And the average will be like everything is kind of in the green area, which is actually dismissing the information that some people kind of suffer from maybe noise levels that are above the requirements, that do not fulfill the legal requirements for noise and noise protection. So this is something you have to think about, because whenever you condense all this massive amount of data into a single number, you lose a lot of information, and sometimes you lose too much. So you can distort the results, and you lose somehow it doesn't really represent the reality or the initial analysis results anymore. So this is something to spend some thought of when you're doing that. Yeah, now back to the example. So we had our simulation engines here, thermal comfort on streets, solar radiation mostly, then the CFD, wind speed, and footfall through quarter. That's weighted between this analysis. We come to that later. And then access to quarter. This is kind of the walking time from all other areas, from all other houses to this quarter. In some cases, we even combined multiple of the simulation. For instance, we took footfall through quarter and weighted the thermal comfort on streets with it. So to say that streets with many people walking through it, according to that simulation, there it's more important to have a target temperature of 20 degrees compared to other streets. So you can also kind of combine these different analysis methods to say, to go more in the direction of welfare analysis. The more people benefit from it, the better, for instance, the more important. Yeah, so on the left-hand side, you see our final performance indicators. Then this is the interface of Octopus. We ran, I think, 2,000 iterations. You see some of the results. And maybe more importantly, the overall trajectory of the optimization process, including the bounds, the min and max values for each indicator, that we then used in the manual design process to say, okay, to kind of just give us the min max values in this radar charts to say, okay, you performed 50% of the maximum, you got 50% of the maximum accessibility score. Of course, some of these targets are kind of exclusive to each other. So probably it's never possible to reach 100%, but nevertheless, it helps to get a feeling somehow where you are in your performance and design space. Now, computational analysis is a wide field. There are a lot of things and indicators we can compute and quantify. Network analysis, space syntax, some mobility routing, or some traffic simulation things. Then more basics, numbers, densities, height, maybe population density estimates, and so on. Then we have visibility analysis, isovis fields, which is also quite interesting. Because there are like really a lot of KPIs somehow derived from something that looks very basic from these kind of maps. And environmental analysis, including solar radiation, shadow, wind, daylight access, maybe watersheds, flooding, risk flooding estimation, and so on. And yeah, a lot of things, obviously. Now I want to show you two things of these next to the CFD we already covered: visibility analysis and then some network analysis. And I will now just briefly cover them, but I will link on the folder I posted on Slack. There are, I think, 4 or 5 Grasshopper definitions, sample definitions, mostly using decoding spaces. It's a good introduction to that. And also links to YouTube videos, each like 10 minutes, which gives you a tutorial on each of these modules. So if you're interested or curious to integrate any of that into your project, then it's yeah, you can just watch the video, I think, and check out the sample file, and this should do it. Yeah, that says visibility analysis. This is essentially some ray tracing. You have a point in the middle, and then you compute how far it can see along these obstacles here. Here, more urban example. For instance, here, this is the measurement point, and you see from here, you can see the whole blue area. In the red, the red area is a very different situation. It kind of tells you something maybe on how you might perceive space and urban space, or even sequences of urban space. Imagine you move this red dot around here and you come to this space, you kind of see it's very narrow, and at some point the view opens up, and so on and so forth. I think in urban design a lot has been written about that, and this is kind of a kind of simple way to quantify it or start quantifying it, or also to measure maybe the degree of privacy in this courtyards here. The dark blue means from all other points, not many of the other points can view into this area, whereas red means it's very exposed. So this is different way of interpreting that. Then there are, I mentioned, there are like different key performance indicators, or like, yeah, so to say, to derive from these things. A simple one is area, where you say, let's take this example with this blue dot here with the blue area. The area is essentially just the area of the viewing range here. So in this case, it's quite big compared to the other design option here, where this blue is much smaller. So you could say the more viewing area you have, the more things you can see from that point, the better view you have. On the other hand, you have compactness among some more. And this is this measures the parameter. So if you have like if you stand in free space, you might have a circle. This is kind of the highest compactness factor. On the other hand, you have like this red example here, where the compactness will be very low, because compared to the area you see, you have a very large parameter. And this means, from the perception point of view, that you have a more complex kind of situation visually, because something is blocking your view, but you can still see narrow corridors pretty far away. Here's another overview of the four different KPIs associated to ISOVIST and visibility analysis. I think it's a good idea if you come up with your own KPIs somehow to try to go a bit in the same direction. Try to ask questions. What does it answer you? For instance, the area indicator says how visible is space to other spaces, or how visible are other spaces to me. And then also think about what a high value mean and what a low value mean, and so on and so forth. Now, when you want to apply them, use them, this is very helpful. This is like a little dummy example. I made up here a design problem that is, how can we evaluate the attractiveness of walking routes through a quarter and the visual experience they provide. The goal is we want to identify a direct and visually activating route from one side of the quarter to the other. And the route with the most potential shall be developed as a new high street. So this could be kind of the brief here. And how do we measure that? Here we came up with, we use some of this previously mentioned ISOVIST measures, namely area, occlusivity, compactness, and obstacle visibility. Obstacle visibility means how many times you can see these point of interest, or buildings of interest. So how from each point on this route, how much of these points of interest do you see from there? So then we have to define, okay, we have our indicators here, but how do we define what is good and what is bad, or what do we want to do with them? For area, in this case, we say high values are preferred because we see more of the quarter. For occlusivity, we say we aim for high values because this means it's associated with visual diversity. And compactness, the one we mentioned before, we aim for low values because this means there is a higher visual complexity, because it means like there might be you have more narrow views. It's not like you have one simple overview, but it's more diverse. Of course, it's really something discussable, I think. You could probably argue in other directions, but this would be one way to say, okay, to transparently say, this is how we want to measure it, and this is how this is kind of related to our design goals. Here's an example of two alternative routes through the quarter and how the ISOVIST areas varies for each of them. So then you could argue maybe, okay, we want the red route or the blue route. The blue one looks a bit more diverse. I would say you have like sometimes open spaces. This is an area value, and sometimes more narrow ones. So maybe this is a nice space sequence you walk through. In the end, you have to kind of argue for that and make your point and interpret the data in that way. Yeah. Now, the other thing I wanted to mention is urban network analysis. And they're quite relevant in cities, of course. Networks define how places are connected with each other, how fast we can reach them, and so in turn, they affect how we move through space. And because of we want to get as fast as possible from A to B, or at least as pleasant as possible usually, that means that we can make assumptions on how people would move through space. Where can we expect high pedestrian frequency, or how accessible particular locations are to how many people would have access to there. And this has further implications because let's say retail and businesses are dependent on being accessible by people and to people, and sometimes also on footfall along a street and storefront. So they probably base their location choice on network configurations, or it's at least affected by that. And these are some of the core ideas of space syntax that can make those kind of predictions only using the network, no other data inputs required. And this is quite attractive because it's super easy to set up. You don't need tons of data on points of interest or whatever. You really just need geometry, and then you can kind of make these kind of predictions. In some cases, there are a lot of validation case studies. It does not always works, but usually in naturally grown town, it's pretty good, and in small towns where a lot of pedestrians are. So two core indicators in network analysis is closeness centrality and betweenness centrality. Closeness centrality is computed as the sum shortest distance from one street segment to all others. So if we essentially count the distance from this segment to all others, which is, let's say 5 kilometers, compared to when you are on the edge, this might be 10 kilometers or something, because you have to walk all the way to this direction. So when you have a high closeness centrality, that means you can from that point reach all other spaces quite easily, and of course the other way around as well. So if you are a shop owner, you probably want to be somewhere with high closeness centrality because a lot of people can walk to your place in a short time. Betweenness centrality is a bit different. It is the number of times a segment is passed by the shortest path from all to all street segments. So we assume that, let's say on each streetman, one person lives, and that person goes to each other street segments once a week or once a day or something. And then we see this red highlights which street segments would be frequented the most. So this is kind of the footfall measure to say on the way to somewhere people most likely pass by this segment, for instance. So this would also be like a very rough traffic estimation, right? You would assume this street segment here would have the highest amount of walking people or cars or whatever on the way to somewhere. Yeah, here again, like a bit but more detailed information. I will link the slides, of course, afterwards. And you can implement these kind of measures in a design process. This is an example. We try to optimize walkability in a quarter. That's another project we had by, first of all, having a fixed street network, but then playing around with a density distribution between the north and the south here. And it's based on the assumption that we have a certain amount of people that can supply a certain amount of shops, of retail. And based on the centrality values, we estimate the attractiveness of different areas in this quarter for these retailers. And in this sense, and then we compute how far the citizens would need to walk there and how walkable this quarter would be based on these kind of micro simulation or assumptions. Yeah, so this is kind of one way to incorporate these theories.
Just a quick question, Josh.
Yeah, sure.
There's one in the chat. What's the definition of places in the metric on the left? Closeness centrality.
Where are you? Wait.
In the Zoom chat.
Pardon, can you repeat?
Sure. What's the definition of places in the metric on the left?
The one we see right here?
I think it's a little bit backwards.
Yeah, let me go back. You know, I have the chat open.
Yeah, you skipped over it, so I think it was like 39-ish, 40 maybe. Yeah, around here. So
here, how many places are reachable in the 10 minutes walk? Places in this, probably you would say street segments. You can, of course, also assign buildings to street segments, or you say maybe amenities, retailers, or like pharmacies or schools, and then you say you would measure how many schools you can reach within 10-minute walk. So this is kind of a more fine-grained. Yeah, you can define it as you want. Places would be the most general one, but you can kind of narrow it down to something you are particularly interested in.
if you have any other questions, guys, just chime in. Wait for a suitable time where there's a pause and just say, oh, I have a question. That's totally fine.
Yeah. And I have the chat now open, so I can see that too. Yeah. Actually, this short video also answered that question, kind of. This is where we, if it loads, exactly measure the access to a particular type of space that is parks. And quite easy, I think, in this way, we just the shortest walking time to the next park for the whole quarter. And then you can add or shift park locations, and you see this metrics updating. Same, it could make sense to any kind of public amenity, library, schools, and so on, to kind of see how can we distribute them in a way that most people have good access to them. Yeah, that was a few additional simulation engines and indicators I wanted to mention here. We will have a look on them in a case study together with InFraReD, tailored on this Barcelona side. And on the other hand, as mentioned, I provided you this 6 Grasshopper sample definitions. Each there's a YouTube video which takes around 10 minutes to explain. The first one shows the basic components of decoding spaces, how you can set up a simple parametric model and compute very basic density metrics such as FAR, GFA, and so on. The second one introduces the very basic network analysis. Third one, ISO-VIST and visibility analysis. And then we have some more in-depth case studies, for instance, how to couple between this analysis and location choice with the optimization engine. Yeah, hands-on. I think I would make a short break here. Or are there any questions now? So far. No? Okay, then I will present what we are going to do in the hands-on session, in Grasshopper mostly. And after that, we make a break before we start the actual Grasshopper session. So now we go back to our site that you can take. You don't have to, as mentioned, but I will take this as an example. The site in Barcelona, you have an industrial area that is surrounded by a residential district here and a bigger residential district here. Here's a train station as well, and quite some retail and stuff going on. So let's start with a bit of analysis. This is our site in the Rhino model. We have a bit of between the centrality analyzed here. Here's, I think, some rail tracks. So there are just a few bridges going over that. And here we have, I found the wind rows online. I just Googled it. And with a wind profile for Barcelona. So we see in this case, there are quite strong winds sometimes from the north. And usually when the wind comes from the south or southeast, it's most of the time rather low, between 2 and 5 meters per second. Whereas from the north, we sometimes really have storms of 20 meters per second, which is quite a lot. And this can kind of inform us what we have to set up in terms of CFD analysis. Let's have a closer look. As mentioned, we have these residential areas here on the top right and on the bottom left. On the bottom left, it looks a bit more bit more vibrant. If you look at satellite images and Google what kind of amenities and points of interest are there, then we have here a bit more shopping and commercial stuff going on. Here's a light rail stop. And as mentioned, we have a strong wind potentially coming from the north, and low wind is usually more coming from the south, as highlighted here. And that can help us to set up the indicators for simulations. So as mentioned, let's start with creating some kind of a bit shallow and generic vision. We want to create an attractive, vibrant residential quarter with high quality public spaces, very generic. But then we come to some strategies here. First of all, we need to provide a certain amount of residential units or GFA. Then we want high pedestrian climate comfort, so it's attractive for people to come there and spend time in public space. You want, of course, good connection to neighboring residential areas. And if you look back, this is kind of the challenge here, right? Because it's a sandwich between industrial areas and separated from the other residential areas by rail tracks, and here kind of a bigger street and so on. Then we want, of course, a good connection to the transit station, that one there, and high footfall through the quarter, which also means that it's kind of integrated when people walk from one way or go from one way, from one area to the other. So this would also help to activate the space somehow, and something we can measure. Now, that are actionable strategies, but not yet that measurable, at least some of them. So for indicators, we have residential units, simple number of residential units. For high pedestrian comfort, we can say no dangerous areas during storm days. This takes into account the windrows. And we could say we want fresh breezes during warm days, especially for frequented streets. So instead of minimizing strong winds or wind at all, that we want to actually maximize it. So we want to kind of block the wind coming from the north, but open up for the south to have low wind speed air coming in and give some breeze there. Then high access to good connection to neighboring areas and to a transit station can be translated into high access or high closeness centrality when we take when we only measure the amenities in transit stations. And again, high footfall through quarter, that's also straightforward. That's essentially between the centrality through the quarter, weighted with estimated population distribution. So we can say we take the building volumes and take this as a weight for the betweenness centrality. Now we can get even a bit more specific. Number of residential units is self-explaining. We just have to kind of come up with a target number. But with this no dangerous areas during storm, we can be more specific, saying we want to minimize the share of areas with wind speeds of more than 50 meters per second during a storm day. That's kind of the Lawson criteria. 50 meters per second is usually then seen as dangerous, where not only uncomfortable, but also a bit dangerous for health. Then fresh breeze during summer, warm summer days for frequented streets. There we want to maximize the average wind speed on public spaces weighted by footfall. And footfall, again, is between the centrality. So we take the wind speed, we take the analysis result of the wind speed. We only sample public spaces from that. And then we weight that with between the centrality from the street segments. So we have to do quite some operations there. We have to get a subsample for public spaces. Then we have to match, to kind of spatially match public spaces. This is these pixels from the result image with street segments to get the weighting. High access to amenities and transit stations. It's more simple. We want to maximize closeness values, taking points of interest as destination. You will see that that's kind of an option in the analysis component. And finally, we want to maximize weighted betweenness values. And here again, as mentioned, we take building volumes as a proxy for population and work as a weight to say, okay, areas with more building volumes, they just emit more people, right? So it's a bit more accurate. Yeah, and that's it from the project brief, from the demo brief. And I think let's take a 10 minutes break. Or any questions now before Yeah, any questions? No. Yeah.
I had one question.
Yes.
So yesterday I tried putting in the location in the web app,
Yeah.
and because we are restricted to 500 by 500, I realized that if we take a substantial chunk of land as site, we don't really have a lot of context to simulate around the site. So are we then considering all the buildings that we are proposing for the simulations, or maybe we can take those geometry into Rhino, or maybe scale the site somehow, or just entirely a new site?
Yeah, I mean,
yes, I was wondering.
yeah. So for the CFT, that's kind of the case, right? You don't get that much context because of this bigger streets.
Yeah.
But yeah, so it's more about what you design there, what you come up
All
with
right.
yourself, or maybe you keep some of the buildings that are there. For the other things I'm going to show, the context is still
Yes.
relevant. Yeah. But yeah, I mean, you can
Okay.
also take another. But scaling it does not work, because if you scale the model,
Yeah.
then you're
Of course,
out of scale and everything is a bit.
Yes, of course. All right. Thank you.
Do we have any other questions before we go on to a break?
I have one question, quick one. We saw yesterday you were showing how we can create models with the Grasshopper plugin in Rhino, and then export and run the simulations on the web platform, right? Is it possible to do the other way around? I mean, if we want to import a location on the web platform and then bring to Rhino the building, so we have the context, and then we can create our model within that context.
As it stands, no. The other way around does work. So whatever you create within Grasshopper, even if it exists beyond your project boundary, and then you send it up to the cloud, you can actually log into the web app and then see all of that geometry there. Of course, your analyses would only ever be applied to that project area though. But no, the inverse of going to the cloud, getting geometry that exists out there in the world and then pulling it back into Grasshopper doesn't exist just yet. The way you would do so is probably just, to go to OSM or other map services yourself, download a shapefile, and develop a workflow in Grasshopper to generate that geometry there.
Yeah, there are, for instance, some plugins like Urbano. I think Theodore was trying that have a pretty good connection to OpenStreetMap. In the end, on InFraReD on the web server, we also query OpenStreetMap, so you would get kind of the same data, but just we haven't implemented that way, as Merit said.
Thanks.
Yeah, you can still do that workflow in Grasshopper, of course. But yeah, if you wanted to upload it and bring it on the web app, it would have its own context. But in Grasshopper, you could use something like Urbano and get a quick context, and then design your things and talk to the model, let's say, inference on your geometry. So before we break, is it okay if I ask, do you have any thoughts? Did you all, first of all, have some time to use the web app, for example? Is there any thoughts, any problems, any breaking issues and stuff like that? Not really for bugs, just like experience, how was your experience? Is it useful so far to use such a tool?
I can say I spent 30-40 minutes yesterday, and was very interesting. Is understanding it takes a little a few minutes to understand the interface, I think, but then once you understand it flows. But I had difficulties jumping from, I think, the second tab to the third tab. I think is the design to the Explorer, jumping, going back and forth between that step, which I think it's kind of why the whole actually tool exists. For me, it was a little. I still didn't manage to like fully understand. For me, it's not 100% clear how to like do the snap and then do a proposal, then go back and kind of jump back and forth. And for me, that was the. I'm still trying to figure it out. I'm sure that there's a way to do it, but for me, it's not 100% clear yet.
Okay, that's great feedback. Yeah, there's not necessarily a way to do it. It might be like that is the wrong way to do it, so we will figure it out. But yeah, it's a nice feedback. Yeah, thanks. Oh, if anyone else had some thoughts, or if not, we can have a break.
I have some question. Can you hear me?
Yeah.
I've been struggling to connect to InFraReD in web platform and also in Grasshopper, but it didn't connect. And I have some issue with the server error in Grasshopper, and also on web platform didn't retrieve the map data.
Okay. As a general comment, this could be down to an internet connection kind of thing, because the web app in itself is actually rather computationally intensive. So it takes a bit of how to actually run. But if you are having difficulties, have you posted that into the bugs channel?
Yes, yes.
Okay.
I've posted a Slack.
I didn't respond to you. Okay. And did you try it just once, or did you try it a few times?
No, I've tried sometimes in different browsers such as Opera or Chrome.
Yeah, I see that now. So rather than taking everyone's time, I might sit down with you personally a little bit after this, and we can see if we can figure out what the issue is. Okay.
Thank you.
Yep. Okay, thanks. I think it's time for a break. Why don't we say we do 10 minutes of break, and then we come back at the time of the hour. Thanks.
Yep. Okay.
Hello, hello, hello.
Hello, everyone.
10 minutes over.
I have a quick question. When we check the wind results on the web platform, it's just interesting to see how you would classify the 0 to maybe 1 meters per second range as area applicable for long sitting. Like, is it just purely because your climate is focused on more relatively cold countries? Like in Singapore, we would, when we start classifying the different ranges of temperature for comfort and especially activities like transient, short stay, long stay activities, is at least the 0 to 1 meters per second is considered uncomfortable for long stay or even short stay. So just curious, what was your thinking behind that?
That's a good question. Like the metric we're using is the lossless classification. So it was indeed started at like, you know, Northern European kind of settings, right? With higher winds and lower temperatures. But still, I think it's applicable everywhere in the sense that it is a wind comfort and not really a thermal comfort. So in Singapore, you would want like air mobility because of thermal comfort, right? Not really because of wind comfort. So yeah, by itself, when you were just analyzing wind comfort without temperature, which is not the best thing, I know, but people do it, right? You would analyze in terms of wind velocity. So 0 to 2 meters per second, if my memory serves, I think that's what it is. 0 to 2.1 or something like that is the long-term sitting, which means, you know, if you're under shade or in a place covered, you can handle the temperature. That's the range of wind that will make you comfortable to sit there for a few hours, have a coffee and read the paper, right? So that's the logic behind it. Of course,
yep.
The nice thing of InFraReD is that we can adjust that. It's a bit harder to adjust it, but we will do it in the app because again, you can accommodate more and more metrics, but you can't really accommodate infinite. So eventually in the app, we will have a custom, you know, and a way to create custom metrics in a way, right? To translate the wind to something else if people want. But you can already do that in Grasshopper though. That's the very cool thing of the Grasshopper integration. So if you get your results and you will get wind factors, we will discuss about that stuff. You can multiply it with your climate file, right? You have some wind velocities and then you can do anything you want with them. For example, if you are in the tropics, you can say, okay, find the hours with less than 1 meter per second, and that's pretty bad because I know we need air mobility for thermal comfort, something like that. I hope that this answers you.
No, it totally makes sense. It missed my mind that it's wind comfort, not thermal comfort, and probably for wind comfort, Lawson's criteria fits best. But when you guys are developing the thermal comfort module, I think in that one, it's more important for the user to set manual ranges because let's say we are using set star, someone else is using PET. Then that gets important. Okay.
Definitely. Eventually, if we do the thermal comfort, I would think would be a UTCI index, and it would
now
include,
it's UTCI.
It will embed the wind velocity inside, so it won't be about wind on temperature anymore. It would be just about felt temperature. So, but it's a very good point that you made. Should we start the presentation? Is there no other, the demo?
Yeah. Okay, yeah. Just somehow a little bit. Okay, so then we jump into Grasshopper. I hope you all found the file. It's mostly the finished file, so I will just kind of quickly go through it. Show a bit more in detail how to kind of extract results from InFraReD and then further process them. Actually, what Theodore said, we can sample the result, raw image or array we get, and then define your very own performance indicators to your requirements into the site. Second. I'll share. Screen one. Okay, so this quick recap. This is kind of what's our plan. We take 2 wind directions and then some more accessibility metrics. Let's start with the wind stuff. Okay, a bit laggy. I think I have to go to shaded. Okay, so I logged into the InFraReD component here. Now for our case, we need to set up the 2 wind directions, right? So I go to InFraReD, where is it? Here, analysis, and I take one wind speed component, and then I want to take one comfort component. You can already connect them here. And in this case, we want to set wind speed and wind direction in a specific way. Let's say the wind speed component we use for the normal day, for the low wind speed day, where we want to have a fresh breeze somehow. So wind speed is, let's put it to 4 meters per second. And wind directions we can put to 0. This is kind of the north, that's a default. And for the other one, this is, look here, this is kind of the low wind scenario coming from the south. Ah, okay, no, wait, this is mixed up. Low wind comes from the south, so we have to set this to 180 degrees. Yeah. And the storm scenario, on the other hand, comes from the north. So take this wind speed, let's set it to 20, so really strong wind. So we kind of more testing a extreme scenario here. 20 meters per second. And then just a slider with a 0 to wind direction. And the other 2 inputs are actually visualization would also allow you in the future, which you haven't set up the connection yet, to specify your own bounds or KPIs. So then you can actually exactly tailor your comfort criteria according to your context and are not bound to this default Lawson values we use right now. Okay, so these 2 things are connected. Then we create a new project. See, it's my 4th try already. That's number 4. I put the rectangle here. This you should already have 0 to 500. So this is kind of for a study here. I found out I think it's better if you drag your model into the 0, coordinate. So this worked most stable so far. Create the project. Then we deactivate this component and rerun the other one. Yeah, it worked. Just maybe it happened to some of you, I'm not sure, you get a timeout. I think there's a cookie handling your authentication that expires after a while. So if you maybe come back after an hour to your computer and then all the components with server that require server connection don't work anymore, that might be because you lost the authentication. Then you just have to kind of reconnect here and then re-authenticate, then it should work again. Yeah, so we have our project. And now we have our snapshot component here, but this time we want to use a geometry pipeline to get Rhino geometry. I prepared this model here. You have it as well. So we have like a layer with buildings on it, and we want to get them dynamically. So when later I draw something on this map or shift something, this should automatically be updated. So I open a geometry pipeline. I specify the name, buildings. And now what I do is actually copying it for a simple reason, because when I draw something in Rhino, this is, I think by default, a BREP, but you want to have meshes. So on the one hand, this component loads meshes, the other one BREPs, and that allows me to safely post-process the geometry in the right way. So the BREPs, if I have any, I will mesh with this component, and then I can merge both streams. Otherwise, you might get a little error there. So now I have the whole context here. all the buildings. I think it's 3,500. 3,500. However, on the web app, as mentioned multiple times, we only kind of consider what's in this bounding box here. So for efficiency, I will just select the buildings that are within this bounding box in the standard Grasshopper way, or maybe with a little buffer. So I create an offset. Let's make it like 50 meters maybe. And here I input the site boundary again. Remember from the project. So now I have the site boundary a bit bigger here. And then we can use, I think the fastest way to do that is to take the volume we might also need later. So I take a volume that also gives us the centroid of the buildings. And then I can take a point and curve component here. Just make sure that the centroid points are projected to the ground. And now this component checks whether the central points of the buildings are within our analysis area. And if they are, this is specified here. If they are inside, then this component returns a value of 2. So I take this check here and say, set the second number to 2. And when that is true, you can see it here, false and true. I can delete all objects that are not within the site. So when I click here, you see only the ones on the site are now selected. And this is then our input for the buildings. Yeah, this successfully ran for seconds. And now we can run the first analysis. Why not? Now with we set 2 analyses, 1 times wind comfort, 1 times wind speed, with custom settings for direction and speed. These are connected here. You see like how funny the logo changes. And yeah, so what you get, what we saw yesterday already, is an image, raw data, here for the wind comfort and here for the wind speed. And we figured out there's some flipping issue sometimes. So we have this component you have as well. This does nothing more than just flipping the image. We're gonna fix that soon, that it's more consistent. But for now, this issue sometimes occurs that the image is somehow flipped. Anyway, so this is the raw output. Then we have 2 more values here, that is KPI names and KPI values. So by default on the server, we compute, in this case, 16 KPIs. That is essentially single numbers on this overall wind speed distribution. Let me just panel this, have a look inside. So for this wind speed, we have different, to target 3 meters per second, we have the loss and wind comfort criteria, comfortable setting short, and so on. We have the median wind speed for the area. We have the 5th percentile, that is the value, the threshold value under which 95% of the wind speed falls. We have histogram as well. We have max, mean, and those basic things as well. So by default, you get all of this results here in the tree structure. And note that for histogram values, we have not 1, but multiple ones. You could draw a histogram in Human UI or wherever you want. Give me a sense of the distribution. Now, if you don't want all of them, you can just create a panel and let's say we're interested in dangerous and uncomfortable wind speeds, make it a list. Then you can just put it to select the KPIs, and then we get only these 2 back as a result. And we see here for and then also in the right order, right? You can like specify the order here, and then you get it in this way as well. that can help sometimes. So for our strong wind speed, for our storm day, we have values in our area of 0.4% danger and 9.8% uncomfortable for this kind of a patch here, according to our simulation. That is the image here. Yeah. So there, this is how we get like this pre-computed KPIs. The other way is we want to compute our own things and maybe apply some filtering, just like sample certain areas, maybe around a tower or something, to be a bit more specific. For that, we use the wind speed, because here we have the raw wind values, and this is much better to use than this categorical wind comfort criteria, because there we also already kind of visualize the wind comfort criteria and don't have the raw values anymore. So that's why we use wind speed for this operation. Now I provided a few components and scripts here that is one way to sample the image, the result data, based on a geometry input. Let me show that to you. So first of all, I give in a bitmap, this bitmap entry. And now we see we have a bit of this flipped image issue. So let me just quickly flip this. And now it fits, right? Whoops. So we kind of I have the wind speeds here, the wind factors I can visualize with Grasshopper points. Now, what happens here is, first of all, we generate a point grid, point cloud inside the area you provide. So in this case, I just use the default side boundary, but I can also use this round shape here. Let's have a look how that looks like. So just connect it here. And then we see I only sample around this specific custom area. And sometimes that can really make sense, like say you have a high rise or something and you have a quite big analysis area and you only shift one building, and then if you sample and analyze the whole area, maybe there's a change percentage-wise by 0.1 or something. So it's much better to convey a message or to understand what actually happens if you focus then on a smaller area. Or as I mentioned before, you can also say you only care about, or you care particular about public spaces. So you can just kind of mask out the public spaces, streetscapes that are important for this wind comfort and exclude the others. So you get more specific and more accurate. And here you can kind of adjust the resolution of your sampling. Now we can go for the whole area for this case. And yeah, geometry, then we get here essentially this is where this sampling happens. In some Python script, we get the color code out of that. In this case, we have this black and white image here, right? So essentially each pixel has the same RGB values, as you can see here, 84 and so on. So what we have to do now is to transform these grayscale values in wind speeds in our case. For now, we're going to make that a bit more accessible in the next iteration of the plugin. For now, we have to remap manually. So we can use this standard Grasshopper Split Rgb component. I think it's found in display here, yeah. To kind of deconstruct the color into channels, alpha, red, green, and blue. Alpha are the building here. So our buildings have an alpha value of 1, which makes them easy to filter out. Because we don't want to sample values under buildings. They don't have wind speeds there, but the model still gives them some kind of values, but that just would distort the result. So what happens here, filter invalid areas under buildings, is that we take the alpha channel to do that. We again check for when in case alpha channel equals 1, equals 0, if it's like transparent, then we remove those sample points from our data set, so to say. We do that both for the value here. We just choose the red channel. You can also choose the other one in this case because it's just black and white. We do that also for the points, so we can visualize it afterwards. If you look under the buildings, you see there are no points under them, right? Because we kind of deleted them, we filtered them. Then we just use the default remap to wind speeds component. And now we have to put our target speeds here. And if you, as you remember, I think we put as an input, so the analysis results coming from InFraReD are normalized between 0 and 1, essentially. And then we have to see what's our wind speed we specified here. It's 4. And yeah, it's 4. Yeah. So this is kind of our maximum value. This is how the model was specified. So you can just go back here and set this to 4. So right now you still kind of have to do it manually, but working on that. Now we have it remapped to wind speed. So now each of these value represents a certain wind speed measured at the point where it was sampled. And this is visualized here. Target, wait. Yeah. We can also adjust the upper value for better, so it's more clear what's going on here. So if you put this to 4, you see a bit more visually clear what's going on. Yeah, you can also create your legend in Grasshopper and so on and so forth. Play around with this a bit. So of course, because it's the low wind speed day, it's a quite low overall wind speed. So now here, this is kind of a visualization, this part. A bit laggy, sharing the screen. No. So here we have a list of wind values. And as mentioned, this is not yet a KPI. It's not yet a key performance indicator, so to say. What we can do now is the most simple way is take an average. We just compute the average, and this would give us something like this. The 0.9 meters per second is kind of the average on a day where the wind comes from the south and blows at 4 meters per second on the height of 10 meters. That's how the model was specified and trained for. Now there are some other, I mean, it's basic math in the end, right? How you do it here. 2 more examples. One is you can compute the bounds, the percentage of values falling into a range. You specify here lower bound, upper bound. So we can say, how about between 0, between 1 and 2 meters per second, just like this. You see just some logical operations here. And then we get 54% of our areas have wind speeds between 1 and 2 meters per second. So this way you can specify kind of whatever you want. Another one, as simple as the other one, is essentially you can specify a target value. Let's say you think 3 meters per second is just the best wind speed in this area. That's why you want to know how much the wind speeds in average diverge from this target value. So you just subtract it, then take the absolute, and then you can get the mean from that, or like maybe an absolute value, or however you think what suits your narrative and also your goals. Yeah. So now we essentially have the first one ready. This is essentially dangerous areas and uncomfortable areas during storm day. We can just have a quick look what happens if I just draw a building here on canvas. Let's make a high tower to see some impact. Updates a bit. Okay, I think you still have to go here and trigger the analysis again. Now you see like some change happened here. That's also reflected here. And instead of 0.04% dangerous area now for the whole area here, it's 0.4%. Sounds not that much, but for dangerous areas, actually quite a bit, and 11% uncomfortable ones. And that average wind speed increased a little bit, not very much, but this is because of the, it's more triggered with high speeds. Now, of course, if you take the average and only a small, this kind of building has a high impact on the dangerous areas, right? But it's still kind of not a very, not a lot of square meters are affected by that, despite where it's affected, it has a big impact. But this is not well reflected by KPIs such as the mean, because they kind of swallow these extreme, they kind of even out all these extreme values a bit. So this is not always the best thing to look at. Yeah. Then the other part is the network part. I prepared it here a bit. I think we're running a bit out of time. So there's a video, I think, linked where you see exactly how to set it up. I just run through it quickly. You have the decoding spaces component, plugin, and some components of street network analysis. First, we have the geometry pipeline to get in to load the streets on the roads and roadside. The layers to Grasshopper here, we kind of split them at intersection. This is important. So we have really segments, and then we process them. This is decoding spaces thing. We create a graph from them. We run a shortest path algorithm, so we know the shortest path from each segment to all others. And then here we kind of compute centrality values to components here. So this one, I think what we visualize right here is between this centrality. Unweighted. Let's play around with the streets for a second. I turn off the wind speed visualization. And now let's remember our target of having a lot of people walking through our quarter, right? So now red indicates there are a lot of people using these streets from A to B. Now let's see what happens if we create new streets. For that, for speed reasons, I will just deactivate our update snapshot component, because now we're work on another thing. Here I go to roadside, and then I create a few streets. And we see how the things change. So we could think also of a bridge location, for instance, and how that would affect things. Note also the wind performance will probably be affected by this kind of street layout. Remember the strong wind coming from the north. So we might think of something having streets in the northern part, kind of making maybe some turns, so you can have buildings here that block the wind coming from the north, and toward the south we can keep it more open. That could be one way to try to optimize wind performance given the scenario we have. Yeah. Okay. Yeah, what you can also do here is, this is like where we load the buildings from Rhino, right? We can use them as a weight for the centrality analysis. So we say where more people live, this is where more movement is kind of coming from. It's a bit more accurate. And for that, we can go back to this volume. We already computed the building volumes here for all buildings, so we can use this here. And then we need also the building points here. What's always like the thing that on the one hand, we have streets here, we have then building central points, and we need to kind of aggregate them to the same spatial unit, in this case to streets. And this happens in this set of components here. Then these are forwarded to the weights of origins. And now we compute the weighted between the centrality, which is slightly more accurate. You see, it's not that much more of a change, but a bit. Especially if we would draw now, just draw to make an example here. I remove this tower properly. This will reduce the betweenness value in this area. No, now a bit more retriggered. Yeah, you see the difference here, I guess. If I build the buildings layer, like a really unrealistically huge building, this would have an effect on the whole area, essentially, if this would be really the case. Okay, now we computed this, but we visualize it here, but we don't really know, we don't really count the unit. It's a bit hard to interpret. So at best for betweenness is to get the value, to interpret the values relative. So you make a base design and then you say, okay, compared to that, I improved by X, Y, Z. You could, for instance, take the status quo before you insert it to the empty site or something with the original street network, and then you save the value. And by internalized data, for instance, and then you see how you perform differently to this initial state, because in this case, it's quite abstract. But anyway, to measure the betweenness only in our analysis area, we do the same as before, essentially. We filter only street segments within our site and count the values of that. So this is, again, prepared here, same procedure with this point and curve method. I just have to provide the building site again. That comes out from project, low project, supplied here. And then here I get, I have 55 street segments in our site. And when I take mass addition, I just sum up all the betweenness values, which in this case kind of makes sense. We just count all people, all people movement, we add it up more or less. And then we get a abstract value of 28.5. And we can see here or like 1.6 million actually for footfall. If I remove this building again, let's see how this changes. It's 1.6 million now. It's what was it before? That's the thing, you need to save the values to remember what was there. But anyway, this is kind of how this process is thought of. Oops, a little laggy. Okay, one last thing. Do we have it here? Yeah. The very last thing is we take this footfall value from our area, the one I was just talking about. It's here, together with the street segment points in this area, with a goal to kind of weight our wind performance at low wind speed dates with the number of pedestrians in these public spaces. So we combine two metrics, two simulation engines in the end to say, okay, where more people are there, comfort is more important. Where more people are frequently going along, there more comfort is important. So you have this extra little bit of accuracy or of thought put into that. And this is again a simple exercise of matching up two different spatial units. In this case, the center points, the sample points from the area, like an array, and the street points. And we say for each for each sample point here to find the closest street. And this is how we do the weighting in the end. So you get the item and we put it in this arithmetic mean, weighted average component that does the computation for us. So here we have the wind speeds and here we have the weights computed from the footfall. And this gives us a weighted mean of 0.8 meters per second compared to 0.9 meters per second when you don't apply this weighted average. Yeah, I hope this show gave some inspiration of how to come up with new KPIs and combine different simulation engines Again, there are in the folder I sent on Slack, there are the links and Grasshopper files where you have all the decoding spaces parts in more detail and very clearly explained, I think, along with videos. And yeah, that was it from the demo. If there are no questions.
Yes. Just a quick one here about the Grasshopper file. Actually, in the centrality, I'm having a red component actually on the is the get path component. I'm just trying to make sure. Yeah, this first one, the big one. Yeah.
This one, yeah.
Yeah. So in the origin, what are you actually adding there?
In the first one, I think if you don't add anything
source,
there, by default, it takes everything. So it says you take either points or lines. And if you take lines, it's usually the segments that are generated here. So then it means all to all. You compute away from all to all. I have the example here with a point of interest, where it's a bit different. Let's visualize this. So if it's all to all, it's kind of the general movement. It's like if you don't have more information of land use distribution, then that's the best, most educated guess you can do. The most simple traffic model, so to say. But yeah, let's check this one out. I just visualize this. Yeah. So now, well, I actually create a point I can drag, then it's even more clear. So set one point. Make one first, okay. Okay, set. Now I put it as a destination. And now it should be, as I move it, you should see like how this kind of now it's like every house, every person in this area moves to this particular, only to that point. Not to all, then you get like more like these kind of specific.
Yeah, maybe I have another version of the code. This
okay, yeah, I have the latest version.
Maybe yeah, I would check that.
Yeah, I had the latest version. I think it's a bit more, it takes more default values. So if you don't supply those, I think it used to not work. Then you had to do like, yeah, like this. But in one of the videos, this is also explained in more detail and not only focus on this network analysis. So it's less cluttered and a good way to start it. Good. Any other questions? If not, I would suggest we make a short 5-minute breaks. And then we probably we discuss a bit what if you had any issues so far, or how your current state of project is in your groups, to make a short round. Yeah, so we let's meet back in 5 minutes, 45.
Okay.
And yeah.
Okay, I'd like to say that we're going to stop the live streaming now, because we're going to go into breakout rooms in a minute. So thank you to everyone who's been watching us live on YouTube. I'm going to stop the streaming now, and I will see you tomorrow.